director of the Passive House Network, and it's great to have you all with us here today for our online symposium, Restoring the Past, Protecting the Future, Decarbonizing Historic Skyscrapers, an in-depth look at the ongoing renovation to NYU's Rubin Hall to the EnerPHit standard. The EnerPHit standard was released 11 years ago in 2012, and there have been many retrofits here in the US since then, but we're just seeing bigger buildings get the EnerPHit treatment, and it's really exciting. Earlier this year, Hotel Marcel in New Haven, Connecticut was certified to the EnerPHit standard. And now we have a real treat, which, this building, Rubin Hall, is a typical New York City pre-war building. There are just so many of these in the city. And to see what's happening through EnerPHit is terrific. Before we get started, though, I want to thank our sponsors, our partner sponsors, 475 High Performance Building Supply, EnerSign Windows, and Wythe Windows. Our champion sponsors, Rockwool, Partel, Rotoblast, Siga, Intus Windows, Swagon, and Zender America. And our sustaining sponsors, Eros Group, B Public Prefab, Certifiers Cooperative, CTA Architects, Home Energy Services, PH Design, and Rebuild. Please find them on our sponsor webpage, and we hope you visit them. And what do our sponsors support? It's really a nationwide network of peer-to-peer knowledge sharing and a common commitment to change business as usual. We're a national nonprofit affiliated with the Passive House Institute and the International Passive House Association. We're part of a global community providing educational events and trainings to build capacity, change conversations, and change the culture of our building industry. We have a membership in regional chapters, and we hope you'll participate. If you support our mission, we're actually in the midst of a fundraising appeal and ask if you might give what you can. A link to our sponsor page should be dropped into the chat. We just came off an incredible conference in Denver, and the sessions will be accessible online until the end of the year. We hope you check those out too. Looking forward, we have many events and trainings coming up, lots of chapter meetings for the different regions, and notably next week is the International Passive House Open Days. We hope you can find a building near you on our website and visit. And if you're not in the US, they are around the world, and hopefully you can find one near you there too. Training is foundational, and there are both tradesperson and designer consultant trainings starting up soon. For our CPHD, if you register early, you can access the material early too and get ahead of the game. If you haven't gotten trained yet, you should. It's that simple. So on to our featured event, in-depth case study. And I'm happy to introduce our speakers and the agenda here today. Cecil Scheib is the Chief Sustainability Officer at New York University, and he'll be providing the owner's perspective. Michael Syracuse, architect partner at FX Collaborative, will dive into the architectural features of this building. Cheryl Saldana, Senior Project Manager at SGH, will focus in on the envelope retrofit aspects. And then the plan is to have a 10-minute break for a quick stretch. After that, we'll come back to Dylan Martello, Senior Building Systems Consultant at Stephen Winter Associates, who will look at sustainability and the EnerPHit standard. Then to close out the presentations, Jeffrey Rios, partner at AKF Group, will discuss the HVAC retrofit plan. Finally, we'll have a panel discussion with myself and the presenters. Please put questions in the chat. I'm sure a number will be answered as we go through and have a good conversation. And then other questions we'll pull into our actual panel conversation. Lastly, there is AIA and PHI credits available. So just email us at community@passivehousenetwork.org. Again, community@passivehousenetwork.org if you'd like to receive those credits. So I'm very happy to hand it over to Cecil.
Thank you so much, Ken. It's a pleasure to be here. My name is Cecil Scheib, as Ken said. I'm a licensed engineer in the state of New York and NYU's chief sustainability officer. I'll note that unfortunately, due to a prior commitment, I won't be here for the panel discussion because I'm actually going to present to NYU students who are studying architecture and urban design. So glad to get to do that opportunity, but we'll miss you here. But put any questions in the chat from the owner's perspective, and I'll do my best to answer them earlier. So I'm going to go ahead and share my screen. That text seemed to work for folks. Great. So here you see Rubin Hall, and you'll hear lots more about the details and the history of this, but it is a historic building. Willa Cather and many other New York City luminaries lived here at different times, now noted for being NYU's last remaining large dorm that does not have air conditioning. So when I go and speak to NYU students and say one thing about Rubin Hall, I can get a chorus of 300 students in a classroom going, no, I see, at me. So let me just say a little bit about NYU, since many folks may know us, but not everyone may. NYU is a private university. In fact, we're the largest private university in the US. We also have sites all across the world. But at our largest campus here in New York City, which stretches across Manhattan and Brooklyn, 200 buildings, about 15 million square feet of built area, 1,800 separate utility accounts, giving our energy engineering time just, I think, a lot of fun. And almost 1/3% of all New York City emissions from buildings are NYU alone, right? So NYU has a large presence in the city. And I think our buildings are really representative of our urban fabric, right? We have multifamily residential buildings for our faculty. We have libraries, we have gyms, we have swimming pools, we have science labs, we have classrooms, we have all the different types of things you see in a city. Our buildings host supermarkets and doctors' offices. So lots of opportunity that what we demonstrate can get shared to New York City and beyond. And as Ken mentioned in the introduction, if you just look at the work the city's done about building typologies in the city, literally hundreds of millions of square feet of high-rise residential of this basic construction type and HVAC scheme. So really a huge opportunity for impact beyond NYU. NYU ranks number 3 on the Princeton Review top 50 green colleges list as of last week when they came out with this year's ranking. When I spoke this morning at the University Senate to share this great news and said, we all love rankings when we rank well. And if we don't rank so well next year, those rankings don't mean anything. It's really about what you do. So that's true, but nevertheless, it doesn't hurt. So what are some of the things we've done that have brought us to that place? Well, a lot of it is about climate. We wrote our first climate action plan in 2009, updated again in 2021. New York NYU committed to New York City in 2007 that we would reduce our greenhouse gas emissions intensity from buildings by 30% in 10 years. So said we promised we'd do it by 2017, and we were able to do it in just 5 years. That was the climate equivalent of planting all of Brooklyn and all of Manhattan in trees. As I said, NYU is big, and I use it as an example for our students. Don't let anyone tell you if you're a young person that change has to happen gradually and slowly over decades. Actually, change can happen very fast. We've since then committed to a net 50% reduction from our buildings by 2025 and to be fully climate neutral by 2040. And we're doing those studies and research now. Rubin is the leading edge, but how do we reduce or in fact eliminate fossil fuels from campus by that time? We also separately have a pledge to reduce our emissions from our food purchases 25% by 2030. Food is 25% of global emissions, and while you serve 6 million meals a year in its dining halls, this is another huge impact beyond our buildings that we can't ignore. But about buildings, which is 99% of our on-site climate impacts, what are we doing to have campus be greener? Well, the way that we've organized things on campus is to mercilessly hit people over the head with the message that our climate friendly buildings are for all of our health, right? As the people on this call have probably heard this type of message, right? Humans spend 90% of our time indoors in cities and in developed countries. Seems impossible to our students or other people, but unless you're spending 2.5 hours outdoors every day of the week, you're spending 90% of your time indoors. Maybe you do on the weekend, but most days we get up in our homes or apartments, we go to work or school and spend the day indoors, and we go home again. We don't spend that time outdoors. So our experience indoors of lighting, air quality, materials, toxics, all these things, noise control affects our mood and our performance. That's why NYU is on the LEED standard. We certify all of our new construction and substantial renovations. We have over 2.5 million square feet certified or registered, over 25 projects. But what does that actually mean for the experience in our buildings? And, because there's a narrative out there that most people have heard. Look, you know, it's going to have to be colder in winter in buildings and hotter in summer, and you're going to be uncomfortable, but we have to do it for the planet. So sorry, it's time to take one for the team because you're all have bad lifestyles and it's time to change that. And, I ask our community when I hear that, I said, who's ever been too cold in the summer in a campus building because the AC is pumping out in summer and you have to bring a sweater? Everyone raises their hand. Who's ever been too hot in winter in a building, especially in New York City, and had the heat pumping out? You might have had to open your window in the middle of winter. Everyone raises their hand. Who's been in a drafty building where you were distracted by a draft? Who's ever been in a building with poor air quality where it's stuffy and you can't focus on your work or your study because your head feels fuzzy and you feel tired and the coffee's not helping, and then you go outside and get fresh air and you feel wide awake again? Everyone raises their hand. All of those things I just said are energy waste. They're poor HVAC control, poor envelopes. They're wasting energy, they're wasting money, and they're causing climate harm. So instead of saying you have to suffer for the good of the planet and the penguins and the polar bears, let's make our campus better and help our community succeed. Yes, that will cost money, but the energy savings will help pay for it and will reach our climate goals. And I think the most important thing here is the study that many of you have seen by Harvard, Syracuse, SUNY Upstate, and others, showing that when you give people better air quality, and this is both envelope and HVAC control in a green building, their cognitive function can double. And look, NYU, this is what we do. We bring people here to think. The role of our faculty and students is to be a world-leading academic institution. Helping them think better is literally our bread and butter, right? So this is an incredible value-added piece for our green building plan for our community that goes beyond all the details you're going to hear here about what it takes to make an EnerPHit building. But the fact that we're focusing on envelope and fresh air delivery, as well as energy use and carbon impact, is hugely impactful for our community. So what are some examples of things that we've done at NYU? Well, about 10 years ago, we had the chance to renovate another student residence known as Rubin Hall, very similar to Rubin you're going to hear about today. Built in the same decade, in the 1920s, also started life as a hotel before being converted to a student residence 50-ish years ago. Also had no AC. Had heavy oil boilers, number 4 oil boilers, spewing out particulates, causing asthma and lung problems and brain problems and everything around the city. Subject to flooding, right? Heavy oil boilers have to go in the basement. This building's not near the coast, so not necessarily worried about coastal flood. But as we found out with climate change, any area of New York City can be subject to surface flooding that can flood basements from heavy rainfall, right? No one is safe from that. And old single pane windows that not only were terrible energy performers, but were loud. You couldn't close them. They let in noise. And NYU students live in some of the noisiest areas here in New York City. Obviously, this is a national audience, but those who are here in New York, 3rd Avenue, Broadway, 5th Avenue, the Bowery, 14th Street, downtown Brooklyn. And what I always ask people who don't work specifically, with sustainability at NYU, but care about students, what's the value to NYU of a student who does better on their midterms because they slept through the night, even though there was an ambulance that pulled up next to the building at 3 a.m. with sirens wailing and left them on for an hour, right? How do you value that? So we found as we retrofit this building, which still uses fossil fuels, but now has light condensing boilers that could be moved up to the roof because they're small and light. It's actually, an electric ready building because we went from a steam heating distribution system to a water loop that could easily have drop-in air source heat pumps on the roof. And going to that water loop let us add air conditioning, right? So now we have a more resilient building. We have air conditioning. We have good windows that close all the way. This building went from number 18 in the student survey about dorms in terms of noise control to number 2 over 1 year when we did that retrofit. And it cut its emissions and energy cost in half, including the fact that it didn't have AC and added AC. So even adding the energy load of air conditioning, which at this point is pretty much needed in New York City for this type of space, still cut it in half, along with the resilience, the comfort, right? So this was a great success story and everyone loved Brittany. So fast forward 10 years, we go to Rubin, right? What are the opportunities? How can we build on what we learned? Okay, this time, no fossil fuels. Let's go all electric. Let's go from a double pane window to a triple pane window. Will that pay for itself in energy savings? Not necessarily. But will it pay for itself in terms of student value, in terms of even better sound control? Yeah, maybe it does. Let's look at ducting outdoor air to the student room so they can truly take advantage of those great windows. And I think if I leave you with one thing from the owner's perspective, in terms of Rubin, I think that this is the key bit. There's a lot of talk about triple pane windows, 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 windows. If your residential building does not have ducted, delivered fresh air to the spaces, people are just going to open the windows for fresh air. And it is pointless to worry about air infiltration or a triple pane window if it's cracked open all the time for fresh air. You've got to think about both sides of those pictures. Now, thankfully, most of you probably don't live like our students, 4 people in a 200 square foot room, right? So you don't have quite the sweat sock smell that our students may be fortunate enough to enjoy. But again, ducting the fresh air in there so they can keep the window closed, whether it's extreme weather, hot or cold, and still have clean, fresh air in the room is incredibly important. These windows are operable. You hear lots about the windows in this call. If it's the shoulder season and nice out and they want to open the window, great. They're welcome to, and that's great. And in fact, we don't want people to lock indoors. Part of a healthy green building is letting people sort of communicate with the outdoors when they want to, but they can keep the windows closed when it's hot or cold out and still get comfortable temperatures and that healthy air quality. It's more resilient because it's so low energy. It will coast through if there's a blackout and the building can't be supplied with energy. It can coast through. This building does have a backup generator, so we also have that capability. But again, because the HVAC is now smaller and lighter, it's been moved from the basement. This building also had heavy number 4 oil boilers onto the roof, out of flood's way. You'll hear about how we're seeking that EnerPHit certification. And this building will, as a result of it going all electric, be 100% reduction in fossil fuel use, potentially 100% reduction in greenhouse gas emissions as New York supplies a greener grid. We're getting a little bit of crosstalk here. If you're not speaking, maybe you could mute to help some of the background noise. And as a result, significant support from both NYSERDA, New York State Energy Authority, as well as our local utility to do this work, because they were clearly focused on how this could be an example for others. Because as I said, hundreds of millions of square feet of building in a similar situation, which is why we're here today, right? We want to share the knowledge, not just the good parts, but the challenges, what was hard about that, so others can learn. So what are the challenges from the owner's perspective? Well, we're fortunate at NYU in that we can close a building for a year because we have students that move in and out every year. So that would be harder in a residential building where you had to find swing space for ongoing residents or work on the building with them in place or minimally disrupted. We have that opportunity. But the cost and figuring out how to squeeze it in are still big challenges. So how did NYU look at the cost? What is the business case for doing this? So of the things we had to do, including that upgrade of the windows. Sure, that costs money. Looking at electric mechanicals instead of fossil fuel-based mechanicals. Sure, that costs money. But the single biggest cost was adding air supply to individual rooms in a 100-year-old building that did not have it. That's the single largest cost. Not trying to downplay the others, which are significant, but that's the single largest cost. And you'll hear more about how we did that. However, bringing that fresh air wasn't just required for our students' health and comfort and for Passive House, but even for our LEED standard, we had to do it. And also, we know that between now and our 2040 goal, we have to electrify. And if not now, when? Because there's no way we want to retrofit a building, in 2023, 2024, and then say somehow before 2040, we're going to retrofit it again and make it electric. That makes no sense. Once you touch it now and do this gut reno, you're not going to touch that building again in the next 15 or 16 years. So this is our chance. So when you look at it all in, and look at the first cost of the retrofit, which, yes, is higher in option B, which is what we're doing, right? That high performance Passive House certifiable retrofit. Look at the energy cost, though. Look at the energy savings, and look the green there. For those who don't know, New York City has something called Local Law 97, in which starting next year, building operators will actually be subject to fines if their buildings exceed predetermined greenhouse gas emission caps set for each building. And this building would have been subject to those fines. So if you look at all of those things and look at the total cost of ownership, we are practically, in fact, if you look at this, look at total cost of ownership, we are less than a business as usual case where we just replace the fossil fuel infrastructure in that building and don't do other upgrades. Over 30 years, we are saving money. Now, we could have saved even more money by just doing the electrification and not ducting the fresh air, forgoing LEED and Passive House. So that was a decision we had to make with open eyes, that the health benefits to students by letting them keep the windows closed and be quieter, as well as the reputational benefits of LEED and Passive House, were worth that extra money. But we had a strong business case versus doing what we would have used to do. And I'll sort of leave with this and just leave with, if there are other owners or people work with owners or owners reps on the call, that I really strongly advocate this 30-year total cost of ownership model. I think paybacks are not helpful, right? Some of these things do have long paybacks, but to look and say, well, what's the payback from going to a triple pane window? Is it 6 years? Is it 8 years? Oh, it's 20 years. Geez, I don't know about the business case. The windows we're taking out were put in 1968, 50 what's that, 55 years ago. So these buildings are infrastructure. We have to look at them for the long term. And being able to say, hey, over 30 years, this certainly is a 30-year retrofit, it's going to pay for itself, right? The energy cost and the other savings are going to pay for itself is so much of a stronger case than trying to put forth these number of years. In fact, I have been successful advocating for projects at NYU where the savings only paid for 85% of the marginal cost for making a more energy efficient building, which is a nice way of saying infinite payback. Energy savings never paid them back, but saying, hey, we're going to have a better building. Our students are going to be healthier. Our faculty and employees are going to be happier, and energy savings are going to pay for 85% of that cost is a pretty good pitch, much better than paybacks. So I'm going to leave it there, work on answering some questions in the chat, and thanks so much.
Great, Cecil. Thank you so much. So Michael Syracuse here, partner with FX Collaborative Architects. We're a firm based in downtown Brooklyn, and so pleased to be sharing this project and information with you, and pleased to be working with NYU and the rest of the team on this. So let me start my screen here. I trust everyone can see that. So let's get into the details here. Rubin Hall being an existing building, we sort of had to set parts and pieces of what we were working with, and only so many levers to pull. A little bit about the history of the building. Cecil mentioned it, but built 1920s. NYU purchased it in the 1960s. It was originally built as a hotel, and it has been student housing since NYU purchased it. Looking at the exterior envelope, which was the major, architectural features of the building and where we could sort of improve the efficiency, we were dealing with a facade that's 20% windows, about 66% solid wall or columns embedded in the solid wall, and about 14% of floor slab that's intersecting that existing wall. And each one of these elements had their own sort of constraints and opportunities, and we had to explore each one of them individually, and I'll get into the details of each one. So the major effort here, Cecil sort of hinted at it, but the windows were a significant undertaking. We were very fortunate to have the photo on the left from 1926, which was a high-resolution historic photo that was a baseline for us in understanding what the original windows were. And they were originally double hung, sliding, wood-framed windows, obviously single pane. And then on the right is the photo of the building just before we started construction from about a year or so ago, and it shows the steel-framed casement single pane windows that were installed in the 1960s. Not historically appropriate, but have had their life on the building and are certainly past their useful life. So that photo on the left, served as a great model for us in all of our explorations. So when we started thinking about the windows, we're wondering, what criteria do they have to meet? What performance criteria? What aesthetic criteria? And most importantly, a big constraint was what historic criteria do they need to meet? Rubin Hall is located in the Greenwich Village Historic District, and in New York City, that means that any alterations to the exterior of the building needed to go through the Landmarks Preservation Commission, a city agency that could opine on the historic appropriateness of everything on the exterior of the building. So we sort of started listing out all the different criteria that influences our selection, and starting with historic appropriateness and landmarks regulations, the operation of the windows, the materials that they're made out of, the configuration, matching that double hung appearance was important. All the detailing was very important to both us and a regulatory requirement from landmarks. The glazing area, we had to very closely match what the original window glazing area was. And then consistency, replacing any of the windows meant from a Landmarks Preservation Commission perspective, we had to replace all the windows on the building. And then when we get into performance, there was certainly the thermal and energy performance was a significant criteria, and meeting the requirements of passive house and the required U value of the window drove us to triple pane glass. The air infiltration requirements of passive house and to keep the mechanical systems as small as possible drove us to an operation that was not a sliding double hung window, but a pivoting window. And that influenced the design of the frame and everything. And then material and durability. Rubin Hall is a 17-story building, and NYU doesn't want to have to go and paint the exterior of the windows every few years, and that drove us to aluminum framed windows as well. And then this being a student residence, accessibility was very important. Meeting ADA criteria was required. So that drove things like the force that one would use to open the window, force on the handle, and then the location of the handle on the window as well, all came into play, and we got very detailed in the exploration there. And then the maintenance and operation of the windows over the life of the building. Again, the material and durability, the not having to paint them drove us to aluminum framed windows. NYU wanted to be able to clean the windows from the interior of the building and not have to erect scaffolding to clean the windows. Ideally have minimal rain come into the building when the windows are open. When a student leaves for class, leaves their window open, and starts pouring rain, we don't want to flood out their room. And then also ideally removable insect screens. So these were all sort of the starting criteria of what we had to think about, and we had to explain it not only to ourselves and NYU and the rest of the project team, but because we were going through Landmarks Preservation Commission, we had to explain all of these criteria and thought processes to the general public as well at public hearings. And we had to sort of head off every conversation of like, well, why couldn't you do this, right? Because Landmarks Preservation have seen passive house buildings before, but typically on the scale of the sort of 3-4 story Brooklyn brownstone, and not commonly on the scale of this building 17 stories tall. So we assembled this sort of flow chart demonstrating our thought processes in why sort of the typical solutions that have been seen previously by the public, by Landmarks, are not viable for Rubin Hall. And this became, a key slide in our Landmarks Preservation Commission and in all sort of project meetings as well. Then we start to think about, well, how do you meet all that criteria in what window configuration, and ideally using a window product that was not completely custom. It was something we were looking for something that was off the shelf that could, be modified a little bit, but not something that was no new extrusions. We wanted to, not have to test a new product. We wanted something that was fairly readily available and, didn't need to go through a whole product development procedure. So we started to brainstorm around the table, what are the different ways a window can operate and meet as many of these criteria as possible. We looked at things like the lower light of the window swinging in a hopper configuration, and found that in a triple pane window, each one of these sashes can be, hundreds of pounds, and controlling that weight while pivoting in is not possible. We looked at a casement lower window operation where the entire bottom sash would pivot sideways. Again, the weight of that sash was too much for the commonly available hardware. I'll mention also one of the key criteria of this was our typical windows were 6 foot by 6 foot squares. So those are large windows for double hung windows as well. And that large size combined with the triple pane, made for a very heavy assembly and influenced all of these operational decisions. We looked at an in-swing awning lower window. There were complications in terms of how one can actually clean that window, especially the upper light and water infiltration coming in if students leave the windows open. And we also looked at an outswing awning lower window. That was not favorable to Landmarks Preservation Commission requirements because it When they're open, they change the character of the window. And again, there are issues with cleaning it from the interior, especially that top light. So we sort of narrowed our choices down to these three, working with two different manufacturers, Wausau and Schuco. Again, eliminating that lower awning window for a variety of reasons, including the complications of getting this sort of pivot at the meeting rail, started to fatten up all that framing, which was not favorable from an aesthetic perspective, but also all that aluminum started to diminish the thermal performance of the frame, and we couldn't meet the passive house thermal requirements. We looked at this sort of hybrid window that pivoted in different configurations than the top and the bottom sashes, and again learned that the framing started to become chunkier because of all of that operation, and the U value of the window was not met. Then we arrived at the sort of final solution was a whole window tilt-turn configuration. And this was a product that Schuco was already developing in a double pane configuration. And we worked closely with them and their engineering department to modify that into a triple pane configuration. So students could pivot the entire window in for ventilation. It could be pivoted sideways in a turning configuration for cleaning with a custodial lock. And it let us achieve a historic configuration look. So we were able to get the planes of glass offset, so it looks like a double hung window when it's in the closed position. So we went through 2 rounds with Landmarks Preservation Commission, heard their feedback, made some adjustments, and then finally got this approved. And I believe we were the first aluminum frame tilt-turn triple glazed windows approved by New York City Landmarks Commission. And I know that's a very detailed accomplishment, but we're super proud of it to have that, and have that as a reference point for future projects as well. Here we see some of the details and elevational drawings. On the left, actually that 1968 historic window replacement, they documented those original windows. We had that as a great starting point in addition to that high resolution photo. You see in the middle the elevation of our new window, which very closely matches it. We have a little bit fatter framing, but that was all within the within what Landmarks allows in terms of a diminished glass area. And then on the right, the section through the window, indicating in yellow some additional brick molds and other trim that we added in response to Landmarks Preservation Commission requirements to make it a little bit more historically appropriate. We had a mock-up, of the window done a number of months ago. This is some photos from the shop that we saw the first windows coming off of the assembly line. You can see these super fat thermal breaks with insulation in the frame, and the window in its sort of mocked up position on the right. These are some of the images we shared with Landmarks of the original windows on the left, the existing casement windows on the right, our proposed windows here rendered, and proud to have the first window installed just a week or so ago on the building now. And it's in keeping, we think, with the original window, and it's going to radically improve the historic appropriateness of the building as a whole. So that's enough about the windows. We can keep going there, but I'll start to focus on that other substantial 60% or so of the building of the exterior wall. And I start with this plan because, as you can see, Rubin Hall is a densely planned building. There's about 650 students in the building, and we were largely not reconfiguring the rooms as part of this renovation. We're doing some improvements to accessibility, new bathrooms, things like that, but we were not moving the walls between the rooms. And importantly, each one of these rooms is typically a triple room as well. So every inch counts. every inch counts. So I bring that up because that really limited what we could do to that exterior wall. Here we see a sort of 3D plan of each room. So each room has 3 students, 3 beds, 3 desks, 3 dressers. So, every inch of that exterior wall, if we furred it out too much, we might lose a bed and lose a student in each room. So it was super critical to meet that bed count and keep this an affordable living option for students. And then we started to do some probes during the design of the project and got into the exterior wall to understand what it was. And we knew that it was hollow terracotta block with a brick face on the exterior, which is very common for a building of this era. But while that's the sort of typical, we understood when we started to do these probes that over the 100-year life of this building and patching and alterations that might be typical, but there were plenty of exceptions. And there was, newspaper patching up some areas, drywall patching up other areas. And you can see from these photos that the existing building facade is anything but airtight. Lots of gaps, lots of holes, and lots of opportunity to have air infiltration. And it was critical that we really reduce the air infiltration to keep the mechanical systems as small as possible. So what we arrived at was a solution of keeping all of that brick and terracotta block in place, and then working all on the interior face of that, and keeping the plaster that's on the terracotta block in place also. We added on a new fiberglass-faced gypsum sheathing on the interior to that, taped all those joints to prevent air infiltration, spray foam insulation interior to that with a few inches continuous and a few inches between studs, a variable permeability vapor barrier interior to that, and then the drywall that's the final finish in the rooms. Critical to tape all of these joints onto the ceiling, onto the floor. On the floor, we built a sort of mini concrete slab to have a smooth surface to install that membrane flashing. And then, obviously the exterior wall is where this all comes together with the window that we supported from steel studs with metal plates cantilevering off because we could not drill into those terracotta blocks because they would not support the weight of the window and the required wind loads. And also the fan coil units that Jeff will get into later are obviously below the windows with the mechanical piping running up along the exterior facade. And this is a photo, I think, of from about a week ago of a similar situation, of a mock-up room showing the window installed, the spray foam insulation installed. You can see on the ceiling some of the sheathing and membrane flashing, and then the mechanical piping risers that will then connect to the fan coil unit that will be underneath the window. Some details of that whole assembly, again, showing the window framing, the insulation, trying to sort of reach that insulation out to be as continuous as possible with the thermal line of the window, and then pulling it into the interior. And that's where we end up. So right now we're part of the way through construction, and windows are in the process of being installed, and super excited to see this project moving ahead. And with that, I'll stop the slide share.
All right, thank you, Michael. So hopefully you're seeing the screen all right. Just to reintroduce myself, Cheryl Saldana. I'm a senior project manager at Simpson, Gumpertz & Hager, and our role on this project was the envelope consultant. So, when we approach any existing building, not unlike this one of the first steps is kind of looking at the existing drawings and getting a sense of the existing envelope systems. We were lucky in this case, NYU keeps really good records, so we actually had some drawings of the existing walls and windows and roofs to kind of use as a starting point. But then, as Michael started to get into, the next step was for us to just walk the building inside, out, roofs, kind of see what the condition is of each of the systems. You can see from this infrared scan shot that I grabbed at a cold February evening last year, there's a lot of thermal bridges in this building. You know, the windows are a big one for sure, but those slab edges, those columns in the walls as well are pretty poor performing. And so we knew this sort of deep energy retrofit project has to work to offset these things. You know, we're going to change the windows for sure and improve those, but some of those slab edges and columns we would not be able to really change. So as we're doing our sort of walkthroughs, we're also, you know, working with the contractor to perform probe openings and kind of confirm what we're seeing on the drawings. And as Michael was kind of alluding to, we found some things that are not shown on the drawings. So we did know that there was going to be terracotta block inboard, and as we were demoing and making these probes, found, you know, that terracotta is pretty brittle. And knowing that the new windows that were going in was going to be triple pane glass. These are much deeper frames, they're heavier. Also, we have a new building code with higher wind loads that we have to meet. Trying to anchor windows to this brittle terracotta wasn't going to work. So we ended up designing interior stud framing that spans from floor to floor. And there's sort of outrigger plates that pick up the load from those windows. You can see some photos here of that hollow terracotta. Again, as Michael's saying, this stuff is not airtight by any means. Another interesting thing we found, just a little fun story, one of our probe openings, we actually found a little calendar here from someone that stuck this into the wall. Kind of gave me an idea that maybe on my projects moving forward, I may want to stick a calendar in for someone in the future to uncover. Looking at the existing windows, so the existing windows are a thin metal frame. They're about 1.5 inches deep, single pane glass. So we had to kind of pay attention to the relationship and the dimensions of the windows with respect to sort of the exterior masonry and sort of figure out what those reveals would be. And then with this new deeper framed window that was going in, make sure that we were matching those reveals, but then also thinking about, okay, where's our waterproofing going to be going, our flashing around the perimeter, our seals, to make sure that we maintain that continuity between the windows and the walls. This is a photo from the outside. We did notice some areas of the building that have, you know, some exterior cracks. This is probably one of the worst locations where a sill stone is cracked. I wanted to show this photo only to mention that there's a whole other design and construction team that is doing what's called a FISP inspection while we started our design process. FISP stands for Facade Inspection Safety Program. A lot of major cities have these facade ordinances that require a qualified exterior wall inspector to do a hands-on inspection of facades that are, you know, public-facing facades, to look for things like this, cracks and spalling, things that, you know, can fall to the street and hurt someone. So, you know, you inspect it and then you design some repairs, replacements to these exterior components. So, you know, our team that was working on this deep energy retrofit and trying to meet EnerPHit had to work very closely with that project team to make sure that we were coordinated with our detailing, right? Especially where, you know, the windows were being replaced. We want to make sure we're coordinated on those details, that we were thinking about and working through the schedule of when the different aspects of the work were happening. And the idea behind this is to be, you know, both, you know, cost effective and also, you know, sensitive to the schedule we had for the project as a whole for NYU. Then another thing up on the roof when we were walking around, there's several of these old skylights. As you can tell from the photo, they are well past their service life. Leaking both air and water, as you could tell from the damaged plaster and bubbling paint there, as well as the corrosion. These skylights also at the ridge, the very top of them, have open vents, and that's to allow, you know, smoke to escape as well if there is a fire event. So that being, you know, an open vent, not really good from an energy airtightness control standpoint. So needed to be kind of dealt with, you know, in this scope. And, you know, this is the idea of why we walk around these buildings and do these walkthroughs and get up close to things, because we want to identify all of these and make sure we're incorporating them, you know, into the project. I think one of the biggest things, sort of risks to projects like this is during construction, the contractor starts doing demo and opening things up, and all of a sudden there's a surprise because they weren't aware of something, and then it kind of slows down the whole project. So getting as many probes as you can early and doing these walkthroughs are very important. Now, summer 2021 was when we started our sort of design phase of the project, but students actually had moved out for the summer, and we had this unique opportunity of getting to do a mock-up of a couple of dorm rooms, actually. So NYU gave us 2 rooms and said, you know, we'd like to see what the proposed finishes are going to look like and the furniture layout. Which is great, but we said, you know, can we use this as an opportunity to test out some of the insulation, air sealing details we're thinking about? And they said, sure, go for it, but you have a tight timeline because students are moving back in at the end of August. So I think we had about a month to 6 weeks to kind of work through this mock-up. But it was a really great opportunity and a lot of lessons learned through this for our team collectively. So the photo at the top is the existing dorm room, and then at the bottom you can see during the sort of mock-up in progress of the finishes and insulation going in. So in that time frame, we knew we weren't going to be able to replace a window, so that's why you see that blanked off. But we actually also performed blower door testing of just these typical dorm rooms. So it wasn't a whole building blower door test to kind of look at all of the details, but it gave us an opportunity to not only kind of see air leakage to the outside, but air leakage between rooms as well. And so when we did the blower door test, you know, we did have to, again, we blanked off that window. We had to seal some of the openings that are intended. So each dorm room has a bathroom in it, and there's an exhaust fan. So we had to bag and seal those exhaust fan paths of air leakage. But when we ran the blower door test before we started the mock-up, the level of air tightness actually was higher than when we were doing the test sort of in progress during the mock-up. And the reason for that, maybe some of you, it's not surprising if I just go back to the first photo here. If you see the plaster and the layers of paint that have been installed over the years is pretty continuous and airtight. So, you know, the terracotta and the brick not being airtight is not a big deal because the plaster itself is a very good air barrier. As soon as you start to break that plane of plaster, as you see in the photo below, now all of a sudden there's way more paths for air to flow around. And this really sort of impressed on the construction and the whole team, really, the importance of paying attention to the details and making sure we sort of maintain air tightness, you know, through all of the connections. Some other lessons we learned. So here is an example of an electrical outlet that was at the exterior wall. So, you know, we did tell the contractor, you got to seal this airtight, but as you can see, it's not just about the junction box itself, but it's its penetration through the wall. And there's that discontinuity you see behind the actual box. So what we ended up doing is actually relocating all of these to interior walls. Not having any of them at an exterior wall. And admittedly, if there was a bit of air leakage between dorm rooms, there's less consequences to that than if the air leak was happening at an exterior wall. Next is the spray foam itself. So for the mock-up, we used closed cell spray foam. It has a higher R value per inch. We were thinking, okay, we could keep it relatively thin because, as Michael mentioned, there's a lot of furniture to fit in. But as you can see from these photos, one of the risks with these spray foam products is shrinkage that can occur while it's curing. You also have to pay really close attention to surface prep so that the spray foam adheres well to all of these surfaces. Speaking of adhesion, the membranes, the tapes that we're using to maintain that air tightness around the board joints that Michael mentioned earlier is really important. We tried a few different membranes. The one on the left, EPDM, did not work well. On the right, an asphaltic membrane with a really good primer had really good adhesion to the plaster. Speaking about the plaster a little bit more here, this is very old plaster. So it's actually horsehair reinforced plaster. And there were areas where it was bulging, it was debonding from, the backup wall behind it. And so in the mock-up, we had asked the contractor, hey, if you find any areas where it's loose, where it's coming off, just, cut that out and we'll do a patch repair there. What the contractor found out is anytime they started to even try and touch this plaster, it was just crumbling right off. So it was one of these things where when you start to touch it, it just unzips very, very quickly. So that's why, from a schedule risk standpoint, we end up using that layer of gypsum board, a 1/4 inch thick gypsum board inboard. So we're just going to encapsulate the plaster, leave it as is, because the time it would take to demo all of it and just throwing all that material into a landfill was just a lot of work, a lot of time, a lot of cost. It was easier to put up just a new 1/4 inch thick chipboard and tape all the joints and seams of those boards instead, make that our air barrier plane, at least our primary air barrier plane. Also through these probes, as Michael kind of alluded to, we found some areas of 3-weight thick brick masonry. So it wasn't all terracotta backup. And the brick itself wasn't always in the greatest of condition. You can see this example here. It's pretty porous, soft brick. So what we end up doing is collecting samples of this brick from as many locations as we could get to and different floors of the building, different elevations to try and get a good sampling. We sent the brick to our lab up in Boston, and they performed all sorts of testing on it. We got things like compressive strength and durability properties, freeze thaw properties, as well as moisture properties, looking at liquid uptake, vapor permeability, things like that. And from that information, we could actually plug the lab test results into a software tool called Woofy. This is an example of one of the ways you can look at the outputs from the software. So what we have here is, 3 weights of brick we've modeled with that interior plaster, and we basically have plugged in all the properties that we tested of the materials. We can simulate on the outside a weather file for New York, and then on the inside, we simulate the interior conditions, varying temperatures and humidities, things like that. And then we can run the simulation and kind of see what's happening, through the cross-section of the wall assembly. How much is the wall absorbing moisture? Is it able to dry out? And so this is just the existing wall as is. And then we simulated 4 cases of adding interior insulation. And we varied the thickness of the insulation, and then we compared closed cell spray foam to open cell spray foam with a variable permeance vapor retarder at the interior. And long story short, we ended up going with the open cell spray foam with the variable permeance vapor retarder, or smart vapor retarder, some people call it that. And the idea there is just, we recognize that the solid masonry wall is going to continue to be a sponge to water. When it rains, the brick, the mortar is going to absorb that liquid water. And then over time, it's going to dry to the inside and to the outside. As we add layers inside, we're going to reduce that drying capability to the interior. But at least with the open cell spray foam, it allows some drying to still occur to the interior. And the properties of that sort of smart vapor retarder, it actually opens up its pores and allows moisture to dry towards the interior during the summer and warmer months, when you have that vapor drive predominantly happening towards the inside. Versus in the wintertime when it's colder and drier, the vapor retarder is more vapor tight, so it acts as a vapor retarder and prevents interior humidity from entering the wall cavity where it may condense on the wall. We've talked a lot about the windows. Here's a couple more photos of what that looks like, but I want to draw your attention to one detail we had to work through as a team. So this is the windowsill detail from our 50% CD set. I know there's a lot of text here, but I'll just draw your eyes to this one element. So this is a three-sided stainless steel metal sill pan flashing. And the reason why we like to have flashing below our windows is that, you know, we do recognize that windows over time do allow water to leak through. Also, the perimeter sealant joint isn't always 100% perfect, and that sealant can fail again also over time and allow water into the space between windows and walls. And so that water comes down to the sill, and we want to have a flashing there to capture and drain that water to the exterior. And the reason why we like to have it as metal is because metal is a more durable material. So as windows are being installed, you know, there's tight tolerances into rough openings, and the metal can just take a bit more abuse. However, this being, you know, an EnerPHit project, we are very much concerned about the surface temperatures at the interior, and, you know, not having it be too cold and introduce a thermal comfort issue or a condensation issue. So Dylan, coming up, will show you some of the thermal models associated with this. But long story short, when we got to 100% CD, we ended up removing that metal sill pan flashing and instead using or upgrading to a more durable waterproofing sill pan flashing below the windows. So instead of a thinner sheet membrane, we went with a liquid applied flashing product that is reinforced with a fleece, with a fabric. That product, when it cures, is just a little bit more, it's a bit tougher, it's a bit more durable. Being a liquid, it also conforms a little bit better to the uneven substrates. So that's all I had for envelope stuff. So at this point, we are going to take a 10-minute intermission break here. So we will see you all back here at about, we'll call it 1:15, and we'll hear from Dylan Martello.
All right, I think we're gonna start to get back going again in a minute here. Want to just give everybody the heads up. Dylan, feel free to share your screen, and we'll wait and just start at 1:15.
Super. Can you see my screen?
Yep, you're right.
Awesome.
Looking good. All right, we're 1:15. Take it away.
All right. Thanks, Ken. Thank you all for being with us here for the second half. Now we've had our sixth inning stretch. I am going to dive into specifically the EnerPHit aspects of this project. I think Cecil did a really good job of kind of diving into why EnerPHit, why Passive House, why this level of sustainability. I'm going to dive into sort of how and how EnerPHit guides the design and comes really as an important factor in making key decisions about the building's design and just testing and verification. Quality control is a big part of that. So I'll dive into that. Real quick, I'm a senior building systems consultant on our Passive House Services team at Stephen Winter Associates. Been sort of a project manager now for about 5 years. Have worked on a couple of different retrofit projects, a lot of unique projects, and this project is certainly up there with in terms of exciting, innovative, trend-setting project, and also one that I personally, and I'm sure the rest of the team can speak for, has learned a lot already and will learn a lot even more going into the phase of really the meat of the construction. So I'm going to talk a little bit about lessons learned and things that can advise us to build better buildings moving forward. Okay, so starting off with EnerPHit. For those of you that are not familiar, EnerPHit is the retrofit path for existing buildings. And within EnerPHit, there are 2 paths you can go. And that is either the performance path or the component path. And what do those mean? So the performance path is essentially the same thing as Passive House Institute's new construction standard, where you have an energy model and you have an energy budget for heating demand and cooling demand. These are before the efficiencies of the heating and cooling systems are factored in. It's solely based on the envelope's performance, as well as your ERV or your ventilation heat recovery performance as well. And you basically just cannot exceed those energy budgets. So as shown here, under the performance path for EnerPHit, the criteria is 6.34 for heating demand. This is in IP units, BTUs per square feet per year. And on the cooling side, 8.24. As you can see, however, we do not meet the performance path criteria because largely of a few factors. One, the fact that we can only really insulate from the interior side, which creates challenges dealing with thermal bridges at slab edges and wall partitions. Also, it's extremely dense with regards to the amount of outdoor air and ventilation needed in this building. So that increases the heating demand. And lastly, we are really only able to insulate from the interior. So that kind of limits the amount of insulation and R value we can actually add to help meet this heating demand. But that said, that is exactly why PHI has what's called the component path. So the component path is a little bit more prescriptive. Prescriptive in quotes, because essentially the way this works is you have performance targets, but for specific components of your building. So for your envelope, they break it down into building envelope to the exterior air, building envelope to the ground. And then they have 2 separate categories, which are really, really, really important. And that's the wall with interior insulation in contact with exterior air and wall with interior insulation in contact with ground. These 2, rows 3 and 4, these 2 buckets or these 2 components are reserved for assemblies that can only be insulated from the interior. And the criteria, which is in the black text there, you can see the criteria for wall with interior insulation these are for walls with interior insulation only. The criteria is less stringent. It's 11.4 as opposed to 18.9 for any envelope that has insulation, not only on the interior, but also in the exterior. So what am I getting at? Basically, we know from a historic preservation standpoint, we can only insulate this building from the interior. That then means the critical threshold for this project under the component path, which is the more feasible path here, is that third row, the wall with interior insulation in contact with exterior air. And you can see I have this out to 3 decimal points in green because that number can move a lot. And one thing that I'm going to dive into a little bit on the next slide, but mention here up front, is that any wall or any surface really that has no insulation or little insulation can extremely impact your overall building average R value, which is what we see here at R12.2 for the walls. If you have like a stairwell, for example, where you can't add insulation, or some of those more challenging areas to add insulation, that can really have a big impact. So we had to factor all of that in as we did both the feasibility study and also the analysis moving through design. A couple of things you'll notice that a couple of these criteria are not being met. So one of them is the building envelope to ground. This is particularly the floor slab. So while the floor slab has an R value, probably about 2 of just basically the existing structure, in order to insulate and essentially renovate the floor slab, that would require an extreme constructability challenges and extreme cost to do that for very little value. There is specific exemptions within the EnerPHit criteria in these situations. The other main one that I want to highlight is the window U value. So you can see the criteria is 0.19. This is a whole window installed U value. So it factors in not only the glass performance and the frame performance, it also factors in the glazing spacer. But lastly, it factors in the window to wall installation detail, what we call a psi value of the install condition or the window perimeter. And one thing that I'll show in a bit here is that that was an extremely challenging detail, and the amount of heat loss contributed from just the install detail alone took this window from about a U.19 to a U.24. So big impact. But EnerPHit has exemptions available for situations like this, where you can only insulate from the interior, and that thus creates high thermal bridging at the install condition. Okay, so the extent of the thermal and air barrier on the left is actually the cellar level. And the reason I wanted to show this was because you can see that we are excluding some spaces from the air and particularly the thermal boundary, but particularly the air boundary. So that red line is the line of continuous air tightness. And we're excluding spaces at the perimeter of the cellar. And we're doing this because if you've ever walked around in New York City, you know, there's a lot of grates in the sidewalk and things that are connected to below grade spaces. And there are multiple of those connections from those perimeter spaces. This is what we refer to as sort of the vault spaces. So within those vault spaces, there are sidewalk grates that are connected to. So I'm going to jump ahead for a second here, and you can see this is an example of one of those sidewalk grates that are connected to the vault space. We can't just seal off the sidewalk. That's not feasible. So we have to create an interior air barrier. So that creates some challenges. One of the other challenges is shown in section. So with this specific project, and you can get this situation, and not just institutional buildings, other buildings that are maybe managed by different groups within the whatever entity is managing that building. And in this case, the penthouse level, which is outlined in blue with the pink highlight, which is part of this building, but it's operated by a separate entity within NYU, and thus as a separate sort of budget structure. As a result, the renovation of that space with regards to the interior fit out, the interior design, the insulation on the interior has to happen at a separate phase. So we have a phased retrofit of this project. The one exception to that is really, I'd say that the windows are being replaced because that's a wholesale Obviously, the windows need to match to an extent, so that is being done in the penthouse, but the insulation on the interior side is happening separately. And what, sort of coming back to the point before about when you have walls that are not insulated and walls that are maybe not insulated as well as the other part of the building, that can really have an impact on EnerPHit compliance. So we could not pass the EnerPHit criteria without insulating those walls. We had to insulate it. So as a result, we had to bake in this phase approach. It requires an EnerPHit retrofit plan for PHI. So there's a whole nother layer of complexity there. If you can do it all as one chunk, it does make it a bit easier, but that's just, one of the challenges we have to deal with on this project. Okay, so sidewalk grades. We did do, and I'm going to get into this a little bit later, a test of the existing conditions for whole building airtightness. So we'll get into those results in a minute, but these cellar spaces certainly play a role. So as it relates to the detailing of the thermal and air barrier, what we're looking at here on the left is a detail and plan view. And you can see at the exterior wall, we have our insulation, our continuous layer of insulation inboard of the studs, and then, or sort of outboard of this, the metal studs actually. And then the metal stud cavity with additional open cell spray foam insulation to achieve the R value we needed to get to meet the EnerPHit criteria. Obviously, as Cheryl's alluding to, there's a lot of taping and sealing needed at the air barrier membrane location, which isn't really a membrane. It's actually a half-inch sheathing layer with seams and transitions taped and sealed. So that's sort of the orange lines there. And then, one challenge that you'll probably see is just inevitable thermal bridging at the partition wall and column where that meets. One thing that's not really shown here is that the partition does have mineral wool in it for acoustic fire rating purposes. So, the thermal bridging is not as significant as maybe it may seem, but it is still a part of the challenge and something that gets factored into the energy model. In section detail here on the right, you can see, again, more of those air barrier transition membranes and taping down to the floor and the ceiling. So what does this look like now? This photo is actually taken about a week ago, and you can see those air barrier transition membranes. You can see that sort of black layer is the sort of finished sheathing, and then the air barrier transition membranes in white. You can see there's a lot of just little tiny sections of tape or transition membrane to help seal any sort of point penetrations or locations for that sheathing layer. But we also have challenges of dealing with pipe penetrations and things coming through that. So one of the things that we are gearing up for, because when you talk about air tightness, not only in a new construction building, but I think especially in an existing building, is it's really hard to see everything. And air tightness doesn't care if you can see it. Air will it will find its way out of it if it can get out. So there's a couple of quality control measures that we're doing. One, and this is actually being done by SGH, is to do an air and water test of the window assembly and sort of including that as best as possible, including that window to wall connection, that key air sealing detail. So that's one test. And if there's any issues with regards to it not meeting or passing the infiltration targets, we can address issues with the detailing now before they go and install the remaining hundreds of windows. The other thing is, and we're hopefully planning to do this in a couple of weeks, is to do essentially an air tightness test like you would do for compartmentalization testing of a dorm room, and check for air leaks both qualitatively and quantitatively. So we'll have theatrical fog to see if air is getting into electrical outlets and out through the facade. on the outside or if it's just getting into neighboring apartments. So we'll really know, I think, in a couple of weeks about how effective this is going. But so far, so good with regards to the quality of the installation, visibly speaking. But we're going to do that testing soon. Okay. From a thermal bridging standpoint, Cheryl mentioned and Michael mentioned that the columns and slab edges are, just, they exist. They're there. They're part of you can see the thermal imaging from Cheryl's photo. You can see those thermal bridges at those partition columns and slab edges. But really the biggest, I think, thermal bridge is at the windows. So the windows themselves are going to be replaced with triple pane, highly insulated IGUs and thermally broken window frames. But the window to wall connection detail that I was alluding to before is really an important part of the window performance. And this is the same detail that was shown earlier by Cheryl. And the sub-sill flashing detail was the one that we looked at a lot. And ultimately, what was determined was that the metal flashing was creating too cold of surface temperatures on the interior side where that flashing kind of legs up. And as a result, the strategy was sort of switched to a more of a membrane approach. Now, what does this look like from a thermal modeling standpoint? This is the thermal bridge model for both the windowsill and the window head. And one thing you can see is, for one, the backup wall assembly, the brick and terracotta, is very much cold, which makes sense because that is that's all outboard of the insulation plane. And what happens here is the insulation plane is not in well alignment with the window. And this is just, again, due to just the card that we have to play with regards to existing buildings. There's only so much we can do. So as a result, insulation is returned as best as possible from the interior spray foam cavity and returned back to the window as much as it can be. And that's being done at the window head and window sill. And then also that flashing material. So what we're actually seeing here is the non-metal flashing condition. And it's still not great when compared to a new construction detail. So one of the metrics that we look at is the amount of linear heat loss associated with this window to wall connection detail. And that linear heat loss here for the sill is the 0.087 and 0.060 for the head. Those are about 2 to 3 times higher than we would typically see for a new construction project. And this is with, I would say close to a thermally optimized detail, given everything that had to go into making this detail work. So this is one of the main contributing factors as to why the U value of the window is, when factoring in these heat loss, is so high compared to the EnerPHit criteria of 0.19. But the window itself is extremely good. It's 0.18 window U value. Now at the window sill, you can really see this effect as well, a little bit closer, a little bit zoomed in. At that window frame to drywall return, you can see that sort of yellow portion. So that's really where the thermal bridging is primarily happening. But as you can see in the detail, as best as possible, we're returning that insulation back to the window, and that is actually helping quite a bit. So these are just some of the big challenges with existing buildings that you have to really factor in and really sort of plan for and model for, and really make the best attempt to get those details as optimized as possible. So this is just screenshot showing essentially the exemption within EnerPHit. And I think I probably belabored this point enough, but yeah, the heat transfer coefficient of windows is increased due to a high thermal bridge loss coefficient, i.e. the heat loss or psi value at the window to wall connection when the window is installed with an offset to the insulation layer in a wall that has interior insulation. That's this exact situation. Okay, so moving on to airtightness. So many of you are probably wondering, okay, like the goal is to get this building to EnerPHit. What does that mean from an airtightness perspective? Well, that is 1.0 ACH50 or 1.0 air changes per hour at a 50 Pascal pressure differential between the outside and the inside. That's measured both in pressurization and depressurization. So whether or not we're pushing air or pulling air, the average of those two values has to be below 1. But what is the current condition at? Well, we actually measured it in quotes, attempted to measure it with as much accuracy as possible. And I think we did really the best we could to get that. But the biggest challenge to actually do this, or I guess one of the biggest challenges to actually do this is, one, do you have enough fans, enough doors to actually physically pressurize the building to 50 Pascals? Short answer is sort of. One of the other big challenges, though, is you have all these existing shafts that will get either retrofit, sealed, depending on the shaft, or have sort of repurposed for the ventilation air. But you can see, you know, this is just 5 of, I'd say, 15 to 20 different locations that were just sources of air leaks and openings through the exterior facade, exterior envelope of the building, that we were worried that we weren't even going to be able to build pressure. So in order to build pressure in any situation, you need some level of resistance. So if there's just a huge hole in the building, like if you look at shaft number 5, for example, that's a massive shaft, and you're seeing the louver, which is just open to that shaft. That louver is actually exists on 3 sides out of the 4. So you're only seeing one of the louvered sides, but there's actually 3 of them. So it's a huge connection to the outdoors. So what we actually had to do and help with the contractor is to tape and seal those off as best as possible so we can ensure we can build pressure.
I don't think we're seeing the louvers.
Oh, sorry about that. Thank you, Kent. So yeah, let me reiterate that. So these are just some examples. Again, the 5 out of the 15 or so locations. These were the primary shafts, but shaft number 5 is the louver that I was referring to, and that's a big shaft, and that was one of the big sort of shafts that we were worried about with regards to building pressure. So it took us about 10 to 12 blower fans to actually run this test. You can see a handful of them, not all of them though. Most of these were set up on the ground floor, which is what you see here. We also had to set up fans on the upper levels to ensure that we're building adequate pressure both at the lower floors and the upper floors. We need to make sure we have, as best as possible, uniform pressure across the building. But we were only able to build pressure even with those shafts taped to about 25, 30 Pascals. So it did require us to extrapolate at 50, which you can do. But I don't think if we did not seal off those shafts, I don't think we would have been able to build pressure to have actual data to really run any sort of extrapolation. So what were the numbers? So we got 60,207 CFM at 50 Pascals. Again, that number was extrapolated from the more or less 30 Pascal or so readings that we got, which translates to 3.38 ACH50. This is with all of the open shafts sealed, of course. So we're about 3.3 times higher than the EnerPHit threshold with those shafts sealed. Then what we did as an extra layer on top of that is we utilized some formulas from the Air Barrier Association of America to estimate the amount of air that would amount of additional air leakage through those shafts that we taped. And what we found was that those shafts would lead to an extra about 2.5 ACH50 for the building. Particularly that big shaft number 5 was one of the big problem points. That shaft, along with the other shafts, would translate, and this is our estimation, of about a 6 ACH50 if all of the shafts were left opened for this test. So we think that this building right now in its current condition, or just prior to construction, I guess, is about 6 times leakier than the EnerPHit criteria. So we have our work cut out for us. That's for sure. You know, like I said, we have these quality control measures to really help get us gaining confidence as we go along. So we're, the window airtightness test, the compartmentalization airtightness test of the room, hopefully in a couple of weeks. We're going to test a couple more windows as the project goes along, maybe spot check with some pressure testing of some tricky areas potentially, to really help us know along the way of whether or not we're going to meet that. We also have checklists developed for the contractor to ensure that every square foot of this building is being inspected properly and treated from an airtightness perspective where it needs to be treated. So it's really an exciting time. Like I said, we work on a lot of unique buildings, and this one is right up there with them in terms of challenging, unique, fun, exciting, all of the above. So yeah, we're thrilled to be on it and working with such a great team. So with that said, I'm going to hand it over to Jeff.
All right, thanks, Dylan. Share my slides here. All right. Yeah. Hey everybody, so I'm Jeff Rios with AKF Group. We were the MEP engineers on the project. So I'm going to talk a little bit about how we did do the HVAC retrofit here. So how we did do both providing the ventilation air that Cecil talked about quite a bit, and how we were able to electrify the heating and cooling systems. So just diving right into it. Cecil, in some of his discussion, mentioned Local Law 97 and alluded to that being a little bit of a driver or a factor in some of the considerations for this design. And really what NYU is doing as a university across the city. Just to, he did allude to it a little bit, but just to give a couple bullet points so folks that aren't from New York understand it. Local Law 97 is a law that was passed in 2019 in New York. What it does is it specifically limits the building emissions for all buildings over 25,000 square feet, which Rubin Hall is, which many of NYU's buildings are, and which tens of thousands of buildings in the city are. So it regulates quite a few of the buildings that we live and work in. There are fines for exceeding those emissions. So this has real teeth to it. There's a penalty in terms of financial penalty. That is some of what Cecil was showing in his total cost of ownership. If you did nothing, there was going to be a penalty for that. And to clarify what the emissions are calculated emissions for all the utility consumed on site. So electric, gas, fuel oil, steam, whatever the source of your utility is, there's a conversion in the law for that utility source into a carbon factor so that you can calculate the total carbon consumed at the site. That this law goes into effect. It was written in 2019. The first year of compliance is next year. So 2024, we're coming right up on this being an active law and really regulating emissions in the city. So it goes into effect next year, and then over time, the limits or the sort of carbon emission you're allowed get more stringent over time. 2024 is the first period until 2030, and then every couple 5-year increments 35, and it's 40 and into 2050. So to talk a little bit about what that looks like for Rubin Hall today, this graph represents the carbon emissions from Rubin Hall today, or really based on 2022 data. You see the green bar there is where the building stands currently, or based on 2022's utility consumption. The orange line that sort of goes down and steps down across time is the emissions limit. So that is showing sort of that each of those periods, each of those time periods, the thresholds and how that goes down over time. You see if the building did nothing, so if Rubin Hall did nothing, the expectation would be for the first 6 years of this compliance path or the law itself, there would be no fine, so it would be safe until 2029. But then starting in 2030 and then throughout the remaining life of the building, there would be significant fines on the order of $150,000 to $250,000 annually. So there's a real significant financial penalty there, and that did factor into why Rubin wanted to do some of the things that they wanted to do, right? This helped make the case for total cost of ownership, and it gives some real teeth to it. So that's Rubin Hall today. And if they did nothing, if NYU had decided to do nothing, where it would look in the future. Again, Rubin Hall today, sort of what's there. A lot of folks have talked about this so far. But it's a beautiful landmark building that has very, very primitive systems, right? So there's no ventilation air. The only heating source is just steam distribution from a fossil fuel fired boiler. And if you have any cooling at all in the student residences, it's just, a simple window unit that may or may not be, properly fit in that space with the windows we have. So it is, it's not a very efficient system. It's certainly not a very carbon friendly system. Does the job. And I think as Cecil had mentioned, it is primitive, but it also is what many buildings in New York City, many residential buildings in New York City look like, including the building I live in. Right, this is not an uncommon system, and not an uncommon way for buildings to be heated and cooled in the city. So the stuff we talked about here and the ways we thought about looking at renovating and replacing some of this are definitely potentially applicable across many buildings in the city. Okay, so that's Rubin today. Rubin tomorrow, and again, we've talked about this a few times. Cecil went through this, but it's worth mentioning again. That's what we have today. We have very limited and primitive systems in the student residences. The end result here is going to be adding and improving a number of systems. So the first, and really, honestly, especially from our perspective, the most challenging was adding fresh air distribution. So mechanically ventilating the entire student residence areas was a real challenge. It was, as Cecil mentioned, the most expensive piece of work that we were doing is in terms of a one-off. And it really was challenging because this is a 100-year-old building that didn't have this system in it. So to snake these ducts through and fit them into the space to be able to provide air was not something that was easily done. We were able to do it by utilizing the existing plumbing chase and shaftways between the bathrooms that exist in each of the student residences. So right now, each student residence has a bathroom. That will be the case in the future. And we were able to utilize some of that shaft area between the two rooms, between the two bathrooms on either side, duct through it and tap out on either side to provide the fresh air to the space. That was critical that we had that, and we were able to reconfigure the plumbing in that chase to fit the ductwork. That it seems to work, but I will say, as we're in construction, we're learning new things all the time, and certain shafts might be 2-3 inches shorter than we thought they were. There's challenges that we're still uncovering now. 2-3 inches may not seem like a lot, but we had a very tight window here to fit this stuff in. So it's required a few reconfigurations of how we distributed air from different units. But it is working, and I think at this point we're past any real surprises with that system. So that was a big part of the work we were doing here, and one of the most challenging pieces. Heating and cooling. Obviously, the building is heated today. It is not cooled today, with the exception of some pieces here and there. So we were going to add central heating and cooling, and not only were we going to add the heating and cooling, but we were going to do it with an all-electric and efficient electric heat pump system, replacing that very old fuel oil-fired boiler system. So adding ventilation air, adding cooling, providing with an electric source, domestic hot water. The building, not surprisingly, has domestic hot water that's heated today, of course, but is currently done so with the fossil fuel boiler. So we're going to maintain that system. The students have that today. They're going to have it tomorrow, but we're going to do that with an efficient heat pump system that actually utilizes the HVAC heating and cooling, the water from the HVAC loop as the source side of a domestic water heating system. So that is what we're adding to this building and what we're looking to do to improve it for tomorrow. So let me talk a little bit about some of the specifics. So early on in this project, we had to really kind of sift through what the HVAC options were, discuss them at a number of different intervals with NYU and the full design team. We talked about a number of different options. These 4 are the ones that we really kind of drilled down on with some significance. We started with sort of the business as usual case. This is what was done in Brittany Hall that Cecil had mentioned earlier on. This is a condenser water fed local water source heat pump in each unit. That system, is a pretty good system and something that we were doing and many folks were doing in multifamily buildings and student residences 5-10 years ago. It's pretty good, pretty efficient system. It did allow Brittany, as Cecil gave an example of, to reduce their energy by quite a bit, but it does still have a fossil fuel boiler as the heat source for that condenser water loop. So It was an option. We did want to consider it just so we were setting the same basis as NYU was used to, but we wanted to really kind of make the case for not utilizing that fossil fuel system. So that was the first option. And then we looked at an air-cooled VRF system. This had some viability. I think it could have worked, but for the scale of the building, the height of the building, and where we had space to put condensing units, it was going to be a challenge. It also had some other negatives that we considered in terms of like the length of refrigerant and amount of refrigerant and global warming potential from that refrigerant that were things that we didn't really love in general. Options 2 and 3 were different configurations of an air-to-water heat pump system, and just different ways of serving the building with hydronic loops. Option 2 was the sort of a hybrid of that air-to-water heat pump system on the roof, but utilizing some of the local heat pumps in the units similar to the baseline. And then option 3 is the option we ultimately ended up with, which is a air-to-water heat pump that provides chilled water and hot water to all of the building, with fan coils in each of the student residences. So they will heat and cool with chilled water and hot water in each unit, and that fan coil sort of goes in place of the steam radiator that is there today. We considered a number of different factors for evaluating these systems over time. We looked, of course, at energy and carbon impact. And we also looked at things like first costs. You might imagine that was a contributing factor. And then, things like maintenance and noise in the room. Cecil talked about the critical aspect here of keeping the rooms quiet. We looked at, how much noise we have and for the units for each of these. What does it look like from NYU's perspective to maintain and service these pieces of equipment? So we looked at it from a number of different perspectives. And one of the first ones we really paid a lot of attention to was, well, just how much outdoor space do we need for each of these systems? It's going to be different. What does that mean? That's always critical. But for this building, it was pretty critical for a number of reasons. The first of which many folks have talked about, this is a landmark building. So anything we put on the building was going to be under scrutiny in terms of what it looked like, what the sightlines were from the street, where it fell. That was going to be something we had to consider. Also, it's a 100-year-old building. Just putting stuff on it that is heavy was a consideration, right? We had to make sure we could fit these things in general. Well, forget about landmarks. We had to make sure we could put them there in the first place. And then the final one really was, air-to-water heat pumps and air source heat pump electric cooling and heating systems are something that is more and more regular these days and critically important to decarbonize our building stock. But the simple fact is they take up more space than a boiler system, right? A boiler system just needs somewhere to burn something and a flue to exhaust that. These systems require more outdoor space, so it was important to kind of set that stage for the whole design team and also for NYU to understand that. So we did look at, we kind of did some very preliminary plans, and we kind of just showed everybody just to understand what that looked like and what it meant from a landmarks perspective and a building space perspective. So this is option 1. That's that cooling tower, pretty isolated. The boiler would be located downstairs, and we had just that piece of that upper right corner where we needed that cooling tower located. So certainly doable. Although I will say this one, the cooling tower was the tallest of the options, and height was actually a pretty serious consideration given the fact that Landmarks was quite concerned with sightline from the street. So height mattered more than it might in other scenarios. We looked at the VRF option. You can see here that this is somewhere on the order of double the footprint of the cooling tower. And we had to not only locate condensing units in that upper right corner of the roof, but also in some other areas around. You're also seeing on this screen the DOAS units, that's our outdoor air systems. Those were kept neutral in the different options as we were looking at them, but obviously those also are taking up space in the roof. And then finally, we looked at this air-to-water heat pump system, which was the system we ended up with in the end. The original plan was to have that upper right corner of the roof with our equipment, and then also we needed a series of modules located in a different area. Initially, we looked at that space on the north side. That seemed to work. Just for context, again, just to kind of set the stage, this was sort of in between the amount of footprint of the other two options. So sort of like the middle case in terms of the footprint on the roof, also the middle case in terms of height. The VRF was the shortest equipment, so less of an impact on sight lines, but did take up the biggest footprint. So air-to-water heat pump sort of in between those two. And again, this it's always important where we're going to put stuff, but on this building in particular, with the landmark considerations, this was a key component that we had to consider. This is where we ended up. So this is sort of the final drawing that went to landmarks. design drawing. All the orange stuff is that's mechanical, electrical equipment we're putting on the roof. There's quite a lot of it, as you see. We ended up with the heat pumps in a similar configuration to what we anticipated in the schematics. We have that upper right-hand corner of the roof. We also have and we ended up with 4 modules to the south of that. You can see them on the roof there. I think initially we were avoiding that area just because that is closer to the street in terms of sightline, but we were able to mask that in a way that was in compliance with the landmark requirements. You see there's also a lot of other stuff up there on the roof, all our outdoor air units or ERV units. Those take up quite a bit of space, as does that big orange chunk in the middle, which is an emergency generator, and the radiator for that generator. I'll talk a little bit about the emergency generator in one moment here. But again, this was submitted to landmarks. A whole mock-up was done of this equipment on the roof for compliance, so that the landmarks folk came out, did walk on the street and look at the view lines as they will be seen in the final complete construction. And again, it passed, and that was pretty critical. We did not have as hard a time as the windows did with landmarks, but certainly what was on the roof was a big consideration as well. Okay, so I'm going to take it back a second here and talk a little bit more about that ventilation area, because that was such a critical component here, and really one of the biggest challenges. I think Cecil kind of went down some of the pathway here of what the discussions were early on in the design, but there was some debate of whether or not to do the ventilation area in the first place. Brittany Hall did not do it, just given the timing of it, and it was at the time not required for LEED. And again, this building does have operable windows. There is a pathway for ventilation and to meet code. But we were very concerned as a team with making sure we did the best possible case scenario. Also, we were designing this building sort of right after the COVID pandemic had hit, and the idea of doing fresh air to each of the units was seemed pretty positive, and a real attractive feature for the students. We also, it's overly critical in the tight building that we're going to have here to have this ventilation here. Most folks in the middle of January or the middle of July are not going to open their windows all the way. In New York City, it's just not terribly comfortable. In addition to being super loud on Fifth Avenue here, it's not going to be terribly comfortable in the middle of the winter or the middle of summer to have wide open windows all night. So we wanted to make sure that if we're going to build this building as tight as we are planning to, we had a way for the students to get fresh air. And also an added concern, I mentioned that each of these rooms have a toilet room and a bathroom with a shower. There's concern if you don't have ventilation and proper exhaust and supply air to make that up, that you could have a mold condition if you don't have a way to ventilate that bathroom. So that was another piece of the discussion that was really going to be an attractive piece here to add that. That was something we had considered early on in design, and we think was a pretty crucial piece of getting the system in. It is required for LEED and Passive House, as Cecil mentioned, but that really, as important as it was, I don't think it was the first and foremost reason that we wanted to put this in. And then finally, we were able to do this in a way that added an additional layer of resiliency. One of the questions I often get asked when we're doing an all-electric building and an electric heating system is, well, what happens if you lose power in the winter? Are you going to freeze out the residents? And the first response I typically have to that is, well, do you, on your boiler system, are all your fans and pumps on emergency power? Because if they're not, then you're not going to have heating anyway if you lose electric. But it is a fair question, and obviously we want to make sure that it's a real positive if we can maintain the space at a nice and comfortable temperature in the event of a long-term loss of power. So one of the design strategies we used was, I mentioned we have that generator. We have an emergency generator in the building. We were able to use that generator to provide backup power to the DOAS systems, so our outdoor air systems are backed up by the generator. What that did was allow us to sort of limit the size of the generator. If we had tried to provide emergency power for all of the heat pumps and all of the heating and cooling systems in the whole building, that generator would have gotten incredibly large. You see that orange box in the center of the roof there. That is where our generator and radiator are located. We didn't have an inch of extra space for an extra kW of generator. So we were limited to what we could provide. This allowed us to provide backup power to those DOAS units, which are separate from the heat pump heating system. They are VRF fed coils. So they have a refrigerant coil in each of those units, and they're separated from the base building heating and cooling. What that does, it allows us to, in the event of long-term power outage, provides fresh air for all the residents and also temper that fresh air. So we're providing a minimum level of heating and cooling. It is not a full, we're not going to be able to maintain 70 and 74 all year round, but we are able to add a little bit of conditioning and fresh air to the space. So in the event of long-term power outage, we're going to maintain what we describe as a habitable space. So something that's reasonably comfortable, and if the unfortunate event of a long-term power outage, you'll be able to stay there. So to show what that looks like, the first thing, this building itself, just with some of the envelope performance and the passive house design strategies, was going to be reasonably comfortable in the winter, no matter what. You see that blue line is what we were predicting the building would look like if you had no power and no heating and cooling at all, no ventilation air, nothing. You see in the worst case scenario in the winter, we're going to dip down into the mid to low 50s. So we're not going to freeze out. It still would have been reasonably comfortable, but a bit cold, and we have no way of providing fresh air in those extreme conditions. It is the blue line in the summer goes way up into the 110 degrees. That, the reality is at that point, somebody's going to open a window, but so that's a little unfair. But it is showing that there is no way to really control temperature in the summer in the event of a power outage. The red line is what the expected conditions are if we were to lose power, and also just provide the minimum ventilation air from those DOAS units that are on the emergency backup. You see there, we're expecting the building to stay somewhere in the mid 60s in the winter, not get any colder than the mid 60s, and in the summer stay below 90. And all of that with some dehumidification and some fresh air to the residents. So, in terms of worst case scenario, if you're to lose power, that's a pretty reasonable space to be in, and a nice thing to provide for the residents. That was another key sort of factor here in designing that system and really providing for the benefits of that system. Just to kind of close it out here with a little bit of a scorecard. We talked a little bit about some of the metrics and some of the passive house numbers. I'm going to add to that a little bit. We're expecting right now 16 lead points. Obviously, the building right now is pursuing lead gold, so that's helping us get there. We have pretty significant operational carbon and EUI savings on the order of 45 to 55%. You see 39 EUI as the current modeled target. Pretty good for a building of this age. There's also some, there is some classroom space on one of the other floors, so it's not purely residents. That helps drive that a little bit, but pretty positive numbers here. And then, Cecil mentioned some of the numbers in terms of incentives. We're over $3 million in incentives from our local utility. It's pretty significant, and certainly helped make the argument from some of these systems. It was a real factor, obviously, in considering these. And then final slide here for me. We talked about Local 97. I showed what the building would look like if they did nothing, and they were, $150,000, $250,000 a year in fines after 2030. The expectation here is after we complete this retrofit, there will be no fines. Certainly, as the graph shows here, no fines in 2024 to 2029, no fines in 2030 to 34. You see past that stage, this is a little misleading. It shows potential of fine after 2035, but let's not factor in there. Right now, the city of New York has released the threshold for emissions after 2035, but they haven't, they have not adjusted the electric emissions factor for the grid. So the assumption is the electricity that we buy to heat and cool and power this building will be cleaner as time progresses. They have accounted for that in 2024 and then again in 2030, where you see that step of that green bar. It's not been released past 2035. So the expectation is, assuming we do get more green power on the grid, that number will continue to drop and we will be safely below any Local 97 fines and really importantly, a compliant and pathway to carbon neutral building in the future, which was really one of the goals here, right? And that's all for me.
Great. Thank you, Jeff. Terrific presentation. Terrific presentations all. we'll all come back here. I think spotlight the bunch of us. Wonderful. Love the deep dive and going into all the different aspects. And I feel like we could be talking about this building for the rest of the day very easily. But we'll take a few questions here. I think I've gleaned some from the chat and wanted to run across some that popped into my mind as well. And so starting, Michael, with you first and going back to the windows and the ever important historic windows and landmarks and the process there. And just wanted to, I mean, you did a really nice job going back and forth with the different options with the operations and everything. And I was wondering, as you were narrowing it down, you ended up with Schuco, you know, looking at landmarks, you're talking about 1/8 of an inch in profile and, you know, depths of the shadow and the operation. And talk a little bit about just working with the manufacturer and you as an architect, like, you know, having worked on historic projects before, having gone before landmarks before, you know, what was different? What advice do you have to give in terms of working with the manufacturer to bring it home?
Yeah, I mean, we were super fortunate to engage with Schuco, who, you know, as I mentioned, had a product that was sort of already being developed for a double glazed situation, but saw the market potential of this project and many projects like it coming forward, and really invested a lot of time getting into the details, you know, early on. And we had those very specific technical discussions pretty early on in the project. And we asked a lot of them, and they were, you know, very accommodating and willing to step up. And having a manufacturer partner like that was critical. And, you know, they did it without the commitment of, you know, they were not locked in as a manufacturer at that time. You know, in other scenarios, you know, a design assist in locking in a manufacturer in an earlier phase, you know, might be another route to go about this, and then you could get someone to really invest in it. But we were fortunate to have Schuco, you know, that we could ask, like, well, exactly where can that handle for the window be, and can you meet the 5 pounds of force and get it below the level? And they said, no, like, you need it, you know, an inch lower, this handle length or whatever. And we had those detailed discussions in, you know, DD and CDs, and we were fortunate to have that arrangement. So, you know, if you don't have that, I think having like a design assist relationship is another way to do that.
Yeah, it was nice to have a sizable order out for them, right?
Yeah, and, you know, they saw this was NYU, and, you know, this design team in Fifth Avenue, and, you know, we would go to seminars like this and mention their name. So I think they saw the value there too.
Yeah, no, absolutely. Good. Cheryl, question for you regarding, like, the masonry looked pretty good from the outside. I mean, there was that cracked sill and a couple like very localized kind of water damage. You know, almost in passing, you mentioned freeze thaw, which is kind of refreshing, rather than like very zeroing in on it. And the insulation level was quite minimal. I think, what was the number you ended up at? 12.2 R for the insulation. And I know there's a bit of a dance between the depth of insulation, the how cold the wall is going to be, how safe it is, and the conversation with PHI. And I'm wondering, to kind of a little bit more in the process with that. Because I was actually surprised that there was so little insulation.
So real quick, Cheryl, before you go, I want to clarify one thing. That 12.2 was the factored in sort of all-in envelope for the entire building.
Oh,
so
okay, average.
Derated a little bit by those walls that could get a little less insulation, or like some shafts that can't get insulation in it. So the actual R value of the wall itself is more closer to like an R18 or so.
Okay.
R18, 19.
And it varies. There's some walls that have different thicknesses on it because of, again, trying to fit the furniture, especially like the corner rooms. One wall may have thicker insulation than another. But kind of back to your earlier point there, Ken. Yes, the exterior brick looks pristine. It looks in great shape, and that is pretty common of buildings of this vintage. The masons, when they're building these buildings, tend to save and use the really good brick on the exterior face because they know that's the one that's going to see the weather predominantly, and then they would save the poorly fired brick and stick that inside the wall. And as you saw from some of our photos, the stuff they used to fill in these walls is not in the greatest condition. So that's the stuff we're worried about, and we want to try and protect. Because as we add interior insulation, now these inner withes of masonry, right, are seeing different temperatures than they have, throughout their life. Previously the walls were uninsulated, so they were not getting cold. They were not getting very wet. But now we're adding that insulation, so in the winter they are going to see some freeze thaw cycles. Yeah.
And to follow up, just talking about what you're going to discover when you start opening these things up. I don't think it was emphasized, but it seems that you actually cut back the perpendicular interior walls. So you had continuous exposure, or no?
That was part of a discussion during design phase of like, do we do this or not? Because these are major thermal bridges, and in an ideal world, we would want to cut those back and run the insulation continuously. But we didn't have that ability from a cost standpoint, a schedule standpoint. Also, these walls, in some cases are fire rated partitions, so we could not have the spray foam and these materials run continuously.
Also, the typical interior walls are also hollow terracotta block, and once you start touching it, the fear was the whole wall would come with it.
It starts to crumble.
Yeah.
Exactly.
Yeah. And is that the reason why you furred the interior walls as well, just because you figured it was in terms of the amount of work running electrical and all of that, or
it
gave us a compelling passive house reason to.
Yeah, it gave us a cavity to again relocate those electrical boxes, for example, and run that through a stud space. Yeah.
Great. So Dylan, on the air tightness, looking at the building and the assembly buildup, we have sheathing going on the whole around the exterior, right? On that, and then with the insulation, and then a vapor barrier, smart variable vapor barrier, is also acting as air tightness layer. Are you utilizing that, or just letting it go to the?
So the primary air tightness layer is the sheathing layer with the taped seams and joints and transition to the window frame. It's tricky with when you have spray foam over existing assemblies, because spray foam can also sort of act like an air seal in many ways, but it's how you deal with those transitions and seams and things like that. It's not always great at effectively dealing with those areas. So the primary layer is the sheathing that's installed just inboard of the backup wall, the terracotta backup wall, with those taped seams and layers. There may be some co-benefits to the spray foam. I don't think the vapor barrier on the inside is really going to give us much of an air sealing benefit other than its vapor control properties. But the spray foam in particular is probably like a little bit of a co-benefit, belts and suspenders kind of thing. But really that primary layer is the sheathing and taping.
And on the, I'm sorry, go ahead, Cheryl.
The vapor barrier is being taped, at its perimeter and joints and things like that. So it will provide a little bit of air tightness benefit, and we would call it like a secondary air barrier. So it helps reduce maybe the air that gets into that wall cavity a little bit. But as Dylan's saying, the primary air barrier from like inside to out is that taped gypboard.
Right. Good. And I wanted to follow up regarding the insulation. Looking at the different studies, 4 different studies between closed cell, open cell. Just curious, the reason not to go with like a mineral wool or fiberglass or some fibrous insulation.
I mean, part of that or a significant part of that was the spatial requirements. And I can't remember how much thicker that would all get, but
a little bit more R value.
You know, a couple more inches and we'd lose a bed in each room and lose, you know, 100 plus students out of the building.
Yeah, it's a tight space.
Tight space, and then also remember the walls aren't totally flat, right? That plaster, that existing plaster is a little bit, you know, uneven. So the nice thing with the foam is, you know, it does kind of fill in gaps and things like that and gives you sort of continuous adhesion to the substrate, as opposed to board products. You end up with little gaps in between the insulation and its substrate, where if there was air leakage that occurs, it can more easily flow between the insulation and its substrate.
So Jeff, one thing that struck me was with the heating and cooling system. You know, one of the great benefits of passive house often is that you don't need to provide the heating and cooling at the perimeter. But we see the units at the perimeter. So I just wanted to hear a bit more of the process of that.
You know, and Ken, quite honestly, we did talk about that early on in design. The reality was that's just where they were going to end up. That's just where the physical space was for them, regardless. So it didn't actually become a super detailed conversation, just because the way the rooms are fit now, they were just replacing that radiator. So we didn't have to dig too far. Yeah, we did not have infinite space, and we weren't going to ceiling mount stuff. And yeah, there's sort of limited options in terms of location.
Right. Also, well, it occurred to me, it's like that's where the perimeter heating risers were, right?
So that's exactly right.
Putting them back in the same place.
Following pathways, and yeah, exactly right. Yep.
To add to that, we have to do it for PHI. Comfort criteria is
because of the
not quite as good. Yeah, exactly.
I cannot emphasize this enough. The comfort criteria under PHI is extremely challenging. I think it's for very good reason. Again, to Cecil's point, creating a comfortable, habitable environment for students is really important. And the comfort criteria is a prescriptive U value that you have to meet. It's roughly around 0.18 to 0.20 BTUs for windows building this size, this climate. And especially with the install heat loss that I talked about earlier, it's causing a U value that exceeds that. So I had to, because passive house too.
Yeah, no, that's interesting. So, I mean, you can get exceptions, right, for EnerPHit, but they come with some consequences, perhaps.
And Dylan, just that is a good point. I forgot, like in all the residence rooms, it was going there anyway, basically. But there were a few areas on the second floor. We have some amenity space and some other spaces that are not student rooms, and we did have to provide some linear air at that for that comfort criteria component. So there was a few areas that sort of, I mean, there was a handful of windows, if that, but yeah, it wasn't exclusively the location.
Right. Right. Well, in terms of comfort, thermal comfort and all, I mean, in the heating and cooling and ventilation system, I'm wondering, looking at this, very high internal heat gains, I'm imagining, with 3 people in a room and everybody's got a computer and you know, Lord knows what, plugged in. In terms of the heating load, I imagine when you mentioned, Jeff, at the end about for resilience, tempering the ventilation air with the heat a little bit, I'm thinking to myself, geez, that's probably enough to get them through, unless it's a really serious storm.
Yeah, and it is. I mean, you know, that slide, I think, you know, most of the year they were, with just the ventilation air alone, it's like 68 degrees or something. You know, it's pretty reasonably warm. Cooling is not the same case, right? Like there actually was a higher cooling load. In fact, because of the way we were doing domestic, so just to kind of, I don't know, you weren't asking this exactly, Ken, but the cooling load relative to the heating load just for space heat was higher. But because we were using these heat pumps as a source side of our domestic system, that added to the heating load in the winter, and sort of the capacity needed in the winter on the air to water heat pumps. I don't know if that makes sense. So it's sort of a combination of the two, but certainly, yes, you're right. I mean, I think the performance of the envelope, there's not a whole lot of heating we need to do at that fan coil in the room. Cooling is a bit more because yeah, these are pretty dense rooms.
Yeah, yeah, and well, and of course the comfort criteria, right, Dylan? It's gonna hit us back again. Great. I guess stepping back again to sort of process, and Michael, it looks like you may be answering a question. Sorry, sorry to interrupt.
No, go for it. Yeah.
Just in terms of the process, architectural process, coming at this retrofit versus other ones, and with the specific targets, working with the team, any discoveries, any words of advice?
I mean, the thing that we didn't mention was I think Dylan said we sort of started the project 2021, but we actually started the project in 2018 and did a feasibility study of Rubin Hall and 2 other buildings of different vintages for NYU. And that was a feasibility study to understand what would it take to meet passive house requirements, EnerPHit requirements for these buildings, and to address local law 97. So that sort of set the roadmap. So we weren't starting from scratch when we started schematic design. We already kind of knew the parts and pieces and what was feasible. And like, yes, it is feasible. And here's the systems you might use. And we kind of had the idea of, possible ventilation systems. So I think starting early, and, it's going to be, 6 years or something from start of that study until opening of the building. So starting early with the feasibility study is key, and understanding those costs and parts and pieces. And in that early study, we might have called up a window manufacturer and said, like, could you do a triple glazed historic looking window? And they said, yeah, sure, we can do it. But it's not until you get into those details of the handle, its location, force, everything like that, and you actually get the engineering department and not the salesperson, that you really understand what's feasible. So I think starting with that early study, but then like really getting into the details and anticipating things to change, is important.
Yeah, no, that's great. And in terms of going forward, I mean, this is such a great example for others to be able to pull on. I mean, like we're saying, this is a really very typical New York City building, and other cities. One thing, Cheryl, in terms of the sequencing, we see the windows going in, but there's still facade work to be done, presumably, and other things. I'm just curious if there is a different type of sequencing or any particular issues with that.
So the facade work actually happened first. So
it was done.
Contractors, like, pretty much, I think they're off the job now. Technically,
wow.
They've completely done all their exterior work. But where the sequencing kind of came in was as they were developing their details and repair scope. They would check in with us, we would check in with them as we were developing the window replacement details to make sure we were kind of in alignment. For example, they had some locations where they had to, clean and repaint lintels above the window heads. So we wanted to make sure, okay, they were cleaning enough so that when we came to do our window replacement, where are our membranes and seals going to be adhering to? Is it going to be adhering to this nice, clean, repaired lintel, or is it going to be adhered to, the unprepared surfaces? So it was, little details like that were important to kind of get into, coordinated and aligned on. And then even the materials. So they were coming in and cleaning and repairing some of those sill stones and redoing the sealant joints, because the sill stones are not one continuous piece. Right. In a lot of cases, there's 2 or 3 pieces. So they had to redo those sealant joints. And our flashing membrane for our window sill was going to have to go over that sealant. So something as simple as like, what sealant are you guys using? Is it compatible? Will our membrane stick to it? And, which contractors sort of responsible for which part of these, and where does your stop and our work start? So yeah, it was a lot of conversations, during design and then submittal phase as well. Yeah.
Great. Dylan, on the airtightness, I mean, this building looks, with the windows going in and holes on the roof besides, hopefully get those sealed up. It looks like a tight building, like it could be a really tight building. You know,
looks so
where do
deceiving.
you think you're going to find the surprises? Like, is there an issue with the slab or columns at the perimeter, or that staircase at the perimeter looked a little, you know, worrisome? Maybe, I don't know.
Yeah.
What's going to cause you problems?
So I think in 3 weeks I'll have a better answer, because we'll have done a test of an apartment or of a dorm unit. But one of the main points of the existing conditions test we did was to sort of identify any of those surprises, get out as ahead of them as possible. And what we found is that a lot of locations in the cellar were leaky. So there were, like, for example, there was a huge pipe just to somewhere. I don't know where it was going to some point. I mean, the cellar is a whole, we could do a whole presentation on the cellar alone. It is very interesting. With a huge hole in it. So we're losing a lot of air through that. That's probably connected to the street somewhere, or who knows. The vault spaces in particular that I referenced, that's where we sort of were reaffirmed that, like, yeah, we need to seal the walls to the vaults and not the exterior of the vault spaces, because the vaults themselves are connected to the exterior via sidewalk grates and things like that. So I think we hopefully got out in front of big surprises, of which I think a lot were in the cellar from that test. We noticed on the first floor there, on the first floor, there's a series of classrooms sort of along the perimeter, and there's an exterior wall. And when you kind of get up into the drop ceiling and look at the wall behind, closed door, or behind the walls and everything, the wall type actually changes from like a tile to a masonry or some different change. And what we noticed is that one of the wall types was leaking like crazy and the other wall type was not. So we were able to flag that classroom for the contractor and say, look, that needs to be treated from an air sealing perspective, or else that's going to cause a lot of air leakage for the final test. So the existing conditions test, can't recommend it enough if you can pull it off, to find those potential surprises. And then, the in situ kind of in progress compartmentalization and window tests that we're doing or have even started should hopefully help uncover any more potential surprises.
Fantastic. I'm going to put money that you're going to be like at 0.7.
That would be amazing. We'll be high-fiving all
around. Jeff, on the system side, I guess what are you doing to throttle it down? Because it is like you need to put very little cooling and heating into a room, right?
Yeah.
Even though it's more than maybe we would like, but it's a little bit.
Yeah, I mean, on the room side, one of the nice things about the system we ended up with is it's a hydronic loop, which is very easy to control in terms of the amount of BTUs we're adding or taking out of the room. So, and I think that is one of the positives of this system compared to the other ones we looked at. Like it's a more easily controlled system than would be a VRF or the hydronic heat pump in the rooms. So it really does allow us to throttle that pretty significantly. And also, just, I mean, this, again, not exactly the question you asked, but one of the things we looked at early in design was, the infiltration numbers that we were just talking about. Like, what does that do for the system size? And how does that save us? And one of the positives of this centralized system was that it had a bigger impact, right? Like when we were able to reduce our loads in the building in large part because of the infiltration reduction, it allowed us to take a few of those modules away. Those heat pumps modules went away, which is a pretty significant savings, where if it was just a VRF unit per room, it's, the VRF units come in certain sizes, right? And unless you're like half of the total load, you may not have you can do like a half ton or a ton, or, like it's limited, where it actually did allow us to throttle back the sizing of those heat pumps as well. So.
Right. And what I don't even know what the question is exactly, but in terms of dealing with such a tight area at the interior with these shafts for the ventilation, air, and how you're navigating that. And then, we all understand that on a good day, maintaining the CFM is tough. And so what do you do to mitigate the potential risk there?
I mean, you're hitting. I mean, this is a challenge, right? And I think it was a challenge throughout design. I mean, I don't know that this is answering your question exactly, but I'll give you a little bit of a story that we just kind of ran into in construction, sort of something that came up and we had to deal with. I mentioned this earlier. One of the shafts that we had been running in the outdoor air in, turns out it's a couple inches smaller than we thought it was, right? Like they get in there, they open it up, they measure it out. Look at that. It's like 2 inches short this way, 4 inches short that way. Okay, on one hand, no big deal. But on the other hand, we'd already purchased the outdoor air units. The fans were already bought. We looked at resizing that. It just so happens that the unit that feeds that shaft was like there was less flexibility in terms of where that fell on the fan curve. So if we were to try to add static on that, it was like even more challenging. So we ended up actually kind of redistributing the air on the rooftop to an additional shaft and like running an additional duct just to do that. So I think, I mean, to answer your question, how do you do it? I think just paying a lot of attention to it. I mean, we really had to pay as much attention as we could to the specifics of where the air was going, how we were sizing those units, making sure we had that covered. And even then, in an existing building, there's things you're gonna uncover that are different than you thought.
We somehow hit like the golden triangle of everything overlapping perfectly. Like we got all the vertical risers into existing shafts, did not have to create any new shafts, which would have been, space, cost, steel, everything else.
And they didn't offset 3 times on the way?
Not 3 times, And we were like just able to fit everything on the roof. If we adjusted the amount of insulation in the walls, let's say we decide not to pursue passive house, but no, and went with a different insulation value and needed to add 2 more heat pumps on the roof, I don't know that we would have had a location for them.
Yeah.
So we sort of had this overlapping of physical constraints, physical space, thermal performance, and everything that meshed just right on this.
That's fantastic. So you needed to do it.
Needed to do it, exactly.
Yeah, it certainly made it easier. That's for sure.
That's great. So this has been wonderful. Great to see the chat going and with the Q&A and our discussion. This has been a fantastic symposium, and kind of exhibition of what's possible and where we're going. When do we expect, I guess my final question here and closing it out is, when do we expect it to be complete at this point?
The students are moving in August 2024.
2024, August. Yeah. That's the deadline.
That's the deadline. They're showing up.
Yes, it is.
All right.
Well, hey, I'll give a shout out because someone mentioned it here. Tishman is the contractor or
yes, good
manager on the job, and they're the ones who are seeing this all through actually in the field with their subcontractors and their team. So we hope to do future sessions of these with them to see how it really all came together.
Yeah, that's great. It is a whole other event in terms of diving into that.
Yeah.
Fantastic. Well, thank you all for presenting and showing this great work. Thank you everybody in the audience for coming. It's been a great afternoon here in New York, and looking forward to more of these projects. And we're looking forward to the tour before the students move in.
Absolutely. Thank you so much.
Thank you. Everybody have a great day. We hope to see you at future events.
Thank you.
Thanks, everybody.
Bye-bye.